Now let's see deadlocks. Deadlock is nothing but a set of processes will be waiting for each other. I think you have already seen the deadlock in the concept of this semaphores. So if one semaphore is taken by one process, and if the other process is taking other semaphore, and if these two processes wait for each other, that is deadlock. Or in general, if you want to see any metaphor, let me say this. Let us say you are asking your dad to buy you a bike, right? A bike, and now your dad is saying that you learn it first, then I'll buy it. But then you are saying that you buy it, then I'll learn it, right? Then it will be a deadlock, isn't it? Now your dad will be waiting for you to learn, and you'll be waiting for your dad to buy, and then so that you will learn. Therefore, it is a deadlock, isn't it? The set of process waiting for some event, so that other one will perform the event, so that you will continue. And this one, it is like this. Your dad is waiting for you, right? To perform, to learn the bike, and you are waiting for your dad to buy the bike, and both of the process are waiting for each other, so that you could continue, right? And now that will be an infinite loop, and this is called infinite starvation, right? So what is deadlock is, if you get blocked for an infinite time, which means there is no one who is going to get you out of that infinite waiting, then that is a kind of deadlock. So the definition is like this. See this? A set of processes are said to be in deadlock if they wait for the happening of an event caused by the others in the same set. Which means there are, let us say, 3-4 processes are in one set, and each process is waiting for the other one to do something, right? And then the other one is also waiting for someone else in the same set to do something, and everyone has got blocked, and these events will never occur, right? Then that is called as deadlock. I'll take examples and explain you. And anyway, starvation is nothing but long waiting, and deadlock is nothing but infinite waiting. That is the main difference between starvation and deadlock. And every deadlock is also a starvation, but every starvation need not be a deadlock. The reason is, after some time, maybe process will come out of starvation and they will get executed, right? Therefore, every starvation need not be a deadlock, but every deadlock is a starvation. Resources and release resources. Okay, one more thing, there is something called as a resource. So a resource can either be a file or a variable or a semaphore or register or CPU, anything. Everything in the computer is called as a resource, right? And now a process will like to use some of the resources in order to complete its execution. And whenever it wants a resource, then it is going to ask the operating system, and if the resource is available with the operating system, it will give it to the process, and process will use it and then release it and complete its execution. But sometimes what happens is, let us assume that okay, first watch this one. A process will request operating system for a resource, and in case if the resource is available, the operating system will immediately grant the resource, and the process will use the resource and then release the resource and then return it back to the operating system. That is what happens if everything is smooth. But sometimes what happens is, the resource which you asked might not be available right now with the operating system because someone else is using it. For example, you know the semaphore. If it is a mutex, and if someone has already performed a down on mutex, that semaphore will not be available for you, right? You are supposed to wait until the semaphore becomes available, kind of it. Or let us say there is only one printer to your computer, and now you wanted to print something, and now you are asking for a printer, but if already someone is using the printer, that cannot be given to you. So until that other process finishes using the printer, you are going to wait for some time, right? That is what happens here. In case if the resource is not available with the operating system is going to delay the process of giving you the resource, and for that delay you are going to wait in a block state. You are going to go into the block state and wait for some time. And in case if you wait in the block state only for some time, then that is called as starvation. In case if you wait in the block state forever, right, then that is called as deadlock. So either deadlock or starvation, you will be in the blocked state. Got it? The main difference between starvation and deadlock is the amount of time. In starvation, you will eventually come out of the block state and you will run after some time, but in deadlock you will never come out of the block state. Okay. Now if this is the scenario, now assume that, so now you understood that a process will do three types of things. One is it will request for a resource, and again it will get the resource, and therefore it will use the resource and then release it. So request, use and release it, right? These three steps are performed by a process on the resource. Now assume that there are three processes like this: P1, P2, P3, and there are three resources like this: R1, R2, R3. These three resources can be printers, or they can be anything, registers or files or whatever you could think of in a computer. Now let us say P1 asked for R1 and it got assigned, which means R1 is with P1, and now P1 and R2, no, P2 wants R2 and it got it, and P3 wants R3 and it got it, right? And now P1, after some time, if it is asking for R2 and R2 is under the control of P1, P2, then P1 is going to wait until R2 is available, right? And at the same time, after some time, let us say R2 is with P2 and P2 now wants R3. R3 is already with the P3, right? Then what happens to P2? It is supposed to wait for some time. And at the same time, if P3 wants R1, right, and R1 is with P1, so every process has taken some resources and they are waiting for some other resources so that they can complete the execution, but the other process is not going to leave it. And if you observe it, there is a cycle, isn't it? Therefore this kind of waiting is called as deadlock. In case, okay, I cannot directly declare that there is a deadlock unless you observe, we examine what types of resources are R1, R2 and R3. We shall examine them first. So let's not call it as deadlock as of now. Let me explain some few points. Now, necessary conditions for deadlock. If deadlock has to happen, there has to be 4 conditions which have to be true always. If you have to have a deadlock. First thing is mutual exclusion. Mutual exclusion means the resources which you are talking about should not allow multiple processes to access them at the same time. For example, printer. If one process is already printing something using the printer, at the same time if some other process also starts printing, then there will be interleaving of both the files, isn't it? That will be chaos. So that kind of resources is what we are talking about, and we are not talking about some resources which can be shared. For example, if there is a file and if many processes want to read it, then they need not use any mutual exclusion, right? They can all read simultaneously. In that case there will be no deadlock. So if there has to be deadlock, then there has to be mutual exclusion, which means only if there is mutual exclusion, then only there could be deadlock. Simple, the reason is simple. Deadlock is a condition in which many processes want the same resources, and since they are not able to get them, they are going to be blocked, right? In case if the resource can be used by many processes, obviously everyone can use it, and they can come out of the deadlock. They need not starve at all if they can access the resource simultaneously. And the second condition is hold and wait. Hold and wait means like this: one process is taking up one resource and then it is waiting for other resource, right? P2 has taken up R2 and it is waiting for R3. So this is the condition for deadlock. The second condition, which means if one process is going to hold some resources and then wait for other resources, then what happens is it is not going to leave the resources which it is holding, and for this resource someone else might be fighting, right? And now this wants something else. That is how hold and wait is a necessary condition for deadlock. And the next one is no preemption. No preemption means while some process is using the resource, you are not supposed to pull that resource out, which means while some process is printing the file, you are not supposed to stop the process and get the printer and give it to the other process, right? If that could be done, then deadlock can be resolved easily, isn't it? You pull out one of the resource from one process and give it to the other one. Now other one will use all the resources and finish it and then release all the resources, and that can be used by other process, right? So no preemption should exist for the deadlock to happen. And finally, circular wait. Circular wait means it is here P1 is waiting for P2, P1 is waiting for R2 in fact, and R2 is with P2. Therefore P1 is waiting for P2, isn't it? And P2 is waiting for R3 and R3 is with P3. Therefore P2 is waiting for P3, and P3 is waiting for R1 and R1 is with P1. Therefore P3 is waiting for P1. So there is a circle here. P1 is waiting for P2, and P2 is waiting for P3, and again P3 is waiting for P1. Therefore there is a circle, so it is a circular wait, and therefore these four conditions are the necessary conditions for deadlock. Understood this? So let me do one thing. I'll explain you with problems. This will be very easy if I take problems to explain. Maybe then we shall see the questions, the other theory questions. Okay, fine.